Lasers have the unique ability to focus light into a tight beam across long distances. Because of this, there have been hundreds of prototypes of laser weapons, but they have never truly outperformed kinetic firepower. Why is that? We'll start with the physics. Ordinary light sources produce incoherent light with differing phase, wavelength, polarization, and direction. A laser produces collimated light that has a single wavelength and coherent phase, and it can also be polarized. This results in a very small divergence angle, allowing the light to converge onto a target at very long distances when focused with a lens or mirror. This is achieved by the unique design of a laser. The pump source excites the atoms of the medium, then the medium produces photons of a single wavelength. As the light bounces back and forth within the cavity, the generated photons match the phase of the existing light through stimulated emission. Non-collimated light misses the mirrors and is lost, leaving only the parallel rays to be amplified. A portion of the light escapes through a partially transparent output coupler, forming the beam. All light still diffracts as it moves through space, and lasers spread in the shape of a Gaussian beam that contains 87% of the energy. This profile is characterized by the location and radius of its beam waist, or the narrowest point of the laser beam. The divergence angle of the laser is a function of the beam waist. In a laser weapon, we set the initial beam waist as the diameter of our directing mirror. A Gaussian beam is an idealized function, and real lasers always deviate from this somewhat because of imperfections in the laser and optical system. This deviation from a Gaussian beam is defined with the m² beam quality factor. For a set beam waist, the real laser has a wider divergence angle than an ideal beam, and for a set divergence angle, as in laser weapons, the real beam waist will be larger. Therefore, the real laser will always be less intense. For an ordinary laser pointer, the beam waist may be located within the laser cavity, causing the beam to diverge immediately, but a laser weapon will use optics to focus the beam waist at a further distance. This system acts as a reverse telescope. Just as a larger primary mirror or lens leads to a smaller image resolution, it also results in a smaller divergence angle and spot size of a focused laser. The half-angle equations here are slightly different because telescopes form airy disk patterns and lasers form Gaussian patterns. To calculate the beam width radius at the focus, or our spot size, we multiply this divergence angle by the focal distance, or the distance to the target for our laser weapon. When we calculate the area, it is proportional to the square of the target range. So the irradiance is inversely proportional to the target range. And there you have it. Like I said in my last video, the inverse square law still does apply to laser weapons. You may have heard that the law does not apply to lasers in the near field, and this is because there is a parabolic relationship within the near field of the Rayleigh distance, labeled 2z sub r here, where the beam area is less than twice the area at the beam waist. For a collimated laser pointer, this can be the area just outside of the laser aperture, but for a laser weapon, this is the sweet spot of power at a distant target zone. The length of this region is only a tiny fraction of the distance to the target, and the secondary mirror can be adjusted to change where this region will be to focus on the target. And this will also change the size of the focus spot. We can see that the area of the spot is also proportional to the square of the m². And this is another challenge for laser weapons. The earliest viable laser weapons use chemical lasers, in which chemical reactions excite the gain medium with megawatts of power. This design requires an unstable resonator to prevent hotspots and to use the full gain medium. This usually results in much lower beam quality, m², and needs additional optics to collimate the beam from its initial donut shape. The most famous of this type of laser is the YAL-1 platform. It was envisioned to destroy ballistic missiles in the boost phase from hundreds of kilometers away and use shortwave infrared like most other laser weapons. A public report from 2003 estimated the m² of the YAL-1 at 1.5 and the power at 3 megawatts. The report also mentioned the obvious fact that the laser could not burn through clouds, which would prevent engagements below the cloud layer and above the plane when high-altitude cirrus clouds were present. For the YAL-1 and all other high-powered laser weapons, atmospheric effects are the limiting factor, so they use adaptive optics to correct for the aberrations. These work the same as they do in ground telescopes, where a laser produces a guide star, the camera detects aberrations, and deformable and fast steering mirrors correct the aberrations in a closed loop. The report estimated the Strel ratio of the YAL-1 adaptive optic system at 0.15 for the worst case turbulence in the engagement envelope. The Strel ratio is a measure of quality of an optical system, and in this case 0.15 means the peak intensity would be 6 times lower than with no aberrations. So the YAL1 had some really impressive specs, but it still ended as a failure. In field testing, the YAL1 shot down a liquid-fueled missile at a classified distance in the tens of kilometers, but failed another test on a sturdier solid-fueled missile and could not destroy missiles beyond 100 kilometers, as was the initial goal. So Defense Secretary Robert Gates canceled the program in 2009, and you can pause to read his quotes about the program if you'd like. After the failure of the YAL1, the industry has shifted away from large chemical lasers. Most manufacturers switched to electrically powered fiber lasers, with the exception of General Atomics, which is developing slab lasers for uses like the 300 kilowatt Army Valkyrie prototype. Fiber lasers work by exciting a gain medium embedded within an optical fiber. This produces very high beam quality, but each fiber is limited to only a few kilowatts. This is overcome with beam combiners, which merge multiple fiber lasers of slightly different wavelengths using a diffraction grating, while only slightly reducing beam quality. These are much more compact and do not require toxic chemicals, but they still need large generators or batteries for mobile systems. Now that we understand all the tech, I'm going to do a deep dive on a modern fiber laser system, and for an example, I'm going to use the Israeli Iron Beam system, which is designed to shoot mortar shells, artillery, drones, and missiles, and things like this as a sort of air defense system. And take all of these results with a grain of salt, because of course I don't have any of the classified data or the actual test results. What you see on the screen now are all the assumed specs I will be using to simulate the iron beam. We will analyze it at 4 different distances, and you can see the size of the spots compared to a 1 centimeter cube here. You'll notice that all of these dots are still really tiny even at the 8 kilometer distance. So when we look at a heat equation simulation of what they do to metal and assume no atmosphere, it is pretty close to the same thing. The 1 kilometer dot has 64 times the irradiance as the 8 kilometer dot, but it only burns through the metal a few seconds faster. So for these short ranges, the irradiance doesn't matter as much as the total power on target. When we add in 1 microradian of jitter, the result is the same. So the commenter in my last video who said that the inverse square law didn't apply to lasers, he was wrong, but he did have a point. And that point is that the limiting factor for these laser systems is the atmosphere, not diffraction. Moving on, I will be simulating how long it takes to burn through these targets shown on screen, because these are what the iron beam is designed to shoot down. For the artillery and rockets, these are spinning targets, so I'm just going to simulate the laser moving back and forth at their circumference and rotation speed on a flat surface, which is close enough. The artillery fuse results in the simulation assumes that the laser can correctly target the fuse, like you see here, which is not always going to be possible. So first, we will simulate all the targets with 0 atmosphere and a Strel ratio of 1 as a best case scenario. And as you can see, even in this idealized setup, the laser could not burn through the artillery shell skin at any distance, but it did burn through the fuse at every distance. The rocket survived at 4 kilometers and beyond. Everything else was killed at every range very quickly. But assuming no atmosphere is not realistic at all, so now we'll be applying the estimated Strel ratios based on the average conditions in the Middle East. There's a nonlinear drop-off here, mainly due to the thermal blooming at these ranges. In the realistic scenario, the results are basically what is advertised. The artillery shell never gets melted, and the rocket only gets destroyed at 1 kilometer. Up to 4 kilometers, the mortar shells and artillery fuses and cruise missiles can get destroyed. At 8 kilometers, it stops working and only the drone gets destroyed. But these are just the average conditions, and now we need to talk about weather. I marked the laser wavelength with the red line, and as you can see, even a drizzle will significantly scatter and degrade the laser over several kilometers. It will be unusable in heavy rain or fog, and it cannot shoot through clouds. Dust and smoke aren't on this chart, but they will scatter the laser as well, and those would be very prevalent on the battlefield. So the iron beam is a very powerful weapon when the weather is good, but I don't think it's reliable enough to actually make the difference in a war on a real battlefield. For example, if they put the iron beam in Ukraine, I think it would eventually get overpowered by the opposing artillery and just get destroyed. And when it comes to shooting the artillery fuse, that really has not been proven in combat, and it's unlikely that they would be 100% successful. Finally, these fiber laser systems are still too expensive to mass produce, and so it seems like conventional weapons still have the edge, even for a system like this. I will say the system does seem super effective against drones, and this was actually surprising to me. Before I made this video, I thought that auto turrets with infrared and radar that shot shotguns at the drones would always be better, but it seems like a system like this could be really effective against drones, especially if it was smaller, maybe 5 kilowatts, and if it was much cheaper and easier to produce. Now, when it comes to ICBM defense, you could see the results in the simulation. It wasn't able to destroy the artillery shell even at 2 kilometers with no atmosphere, and so it would really stand no chance against an ICBM reentry vehicle that would also be moving much faster, and that would be going through that 8-kilometer range in just a fraction of a second. And the same thing would be true for a space laser that's trying to shoot at these reentry vehicles during the coast phase. And so I hope that clears things up, because I got a lot of comments on the last video about trying to use lasers to shoot down ICBMs. Now let's move on to the most interesting application of laser weapons, space lasers. First of all, satellites are extremely vulnerable compared to all these other objects we've talked about. So for the structure, they usually only use 1 millimeter or so of aluminum because they're optimizing for weight, and for tracking, they're in orbit, so you always know their exact trajectory. So let's first imagine if we put a system like the Iron Beam in the Atacama Desert and assume it gets a 0.8 Strehl ratio. Its spot size will have a 1.4 meter diameter, so the irradiance will be 16.7 kilowatts per meter squared before atmospheric losses. So this is only around 10 times the irradiance of the sun. For a 500 kilometer satellite, this could definitely do major damage to sensors, but this is not enough to melt through the aluminum. So you need to bump up the power to 800 kilowatts, and then it still takes 30 seconds to burn through just 1 millimeter of aluminum. And of course, some satellites will be thicker or harder to blast through in some ways. So the inverse square law really starts to matter at these distances, and it really requires us putting the laser into space to get closer to the target. In a low Earth orbit, it would get within 100 kilometers of other satellites all the time. Or you could have a satellite actually maneuver around geostationary orbits with a little bit of fuel. Now, a 100 kilowatt system is probably as big as we could go in the near future. The whole Iron Beam system weighs 12 tons on land, and a 40 kilowatt hour battery would be around 300 kilograms more, plus a few hundred kilograms for solar panels. We can also assume it would be lighter if they designed a space equivalent of this. However, cooling would be an issue and would probably add a lot of mass as well. This could then support 60 seconds of pulses while only draining a small fraction of the battery. Here is a simulation for a 100 kilowatt space-to-space laser, and here we assume the Strehl ratio is 1 since this is in space. And the laser would start burning the satellite insides in only 2 seconds at 50 kilometers, and could even burn through at 200 kilometers in 35 seconds. Some satellites that are out of plane or at different altitudes would be harder to reach or to get in range with the laser, but in my opinion, a 100 or 200 kilowatt laser would eventually be within range of almost every satellite in low Earth orbit at some point. If you wanted to go after satellites in higher orbit, you would need much more propellant to maneuver around and get within range, but it would still probably work. So this would be a way to fight wars in space without creating tons of dangerous space junk. But of course, this would violate the Outer Space Treaty and cause a major international incident if it was ever actually used. So I don't think anyone should really do it, but I think it would be really cool. So I'm going to end it there. I hope you guys learned something new, and make sure to leave any thoughts or disagreements or ideas that you have down in the comment section below. And of course, make sure to like and subscribe. And with that being said, have a great day.